In this video, we'll be learning about Faraday's laws of electromagnetic induction and motion EMF. Okay, so before we start, let's have a brief idea about the concept of magnetic flux. So, magnetic flux is basically the measure of the magnetic field lines passing through a given surface. So, if I'm calculating the differential flux passing through a differential area ds and under a magnetic field B, so all I have to do is to the d phi is equal to the dot product B dot ds. So this, in this case, the phi net will become integral of d phi, and that will become the surface integral of B dot ds, and B dot ds is a dot product that will give me B ds cos theta. So this phi net here, this becomes B dot ds cos theta. And if B is uniform and theta is not changing from point to point, then I can this take B cos theta outside of the integral, and all I have to do is just integrate this ds, and I'll get the value of phi net. Okay, so that means if we have surfaces like this, and let's say the magnetic field is in upwards direction, and the magnetic field value is B, and this is a rectangular shape, this is L, this is B, and if I have to calculate the flux net passing through this surface, then F net will be integral of B dot dA or ds, and the surface integral, and B is constant in value and in direction, so B goes out of the integral, and integral dA surface integral, and this is basically the L into B L into B. This is your net flux. Remember that here the theta between the area vector, this dA vector, and the B vector is basically 0. The theta is 0, so cos 0 is becoming 1. So this is an example of surface integral where we have to calculate the phi net. Similar case will be something like let's say I have this circular area, and the magnetic field is in the same direction, B upwards. So if I have to calculate the phi net in this case, as you can see, the angle between the area vector dA vector and the B vector, that is 90 degree. So whatever we do, we have to calculate this cos 90, because this is basically B dA cos theta and integral of that, so cos 90, that is becoming 0. So basically everything becomes 0. The phi net, the net flux passing through this surface, is 0. As you can see, if the surface is parallel along the magnetic field line, so no magnetic field line will ever cross at any point of this plane, and in this case all of the magnetic field lines is this is perpendicular to the surface. So here we have, in this case, we have this phi maximum flux is passing, and here in this case we have this case phi min, and this is corresponding to theta is equal to 90, and this is corresponding to theta is equal to 0. Okay, so let's talk about Faraday's laws. And Faraday's first law says that changing flux in a loop will result in a induced EMF produced in the loop, and the magnitude of the EMF induced will be proportional to the rate of change of that flux. So what it basically says, that if in any loop, if there is a change in the flux, and that could be that change could be because of the change in magnetic field or the change in area, and EMF will be induced in a coil, and that magnitude of the EMF induced will be proportional to the rate of change of the magnetic flux. The second law says that the induced EMF is produced in such a way that it tries to nullify the effect of the external magnetic field. So let's say in a loop the magnetic field is increasing, so in the loop the induced EMF will be in such a way that it will try to decrease the external magnetic field, and if the magnetic field is decreasing, and it will try to increase the external magnetic field. We will talk about these concepts in in a more comprehensive manner in the forthcoming videos. So first let's try to understand what this Faraday's law try to say in a mathematical form. The first law says that E is equal to the induced EMF. It is given by the rate of change of flux. Okay, so we have this E mod, this induced EMF is equal to the rate of change of flux. So let's say I have this area phi, area A, and I have this magnetic field B that is going upwards. And let's say this magnetic field is changing with time such that Bt is equal to B naught t square, where b naught is some constant and this is a function. So if I have to calculate the induced EMF in this coil, I can just write it down as E is equal to d by dt of phi, and we have this phi is equal to b into a. Here cos 0 is equal to 1, that is bt into this area. So this d by dt of phi, that is bt into a is constant, so it goes out of the differentiation. D by dt of bt, and differentiation of this dv by dt is basically 2 b naught t. So what I can write, a into 2 b naught t. So we see this E is also a function of time, and that is given by 2a b naught into t. This EMF induced is increasing with respect to time. And let's say if this b was a constant value, if this b was a constant value, then we would have this E is equal to d by dt of b, simply b into n, and this there should be a constant value since b is a constant. So all we'll get is E is equal to 0. That means if there is no change in flux, no EMF will be induced in the coil. Now let's apply what we have learned so far in this case. There is this loop is there, and a resistance is attached, and there is this wire that can slide over this this set of wires, and this wire is going forward with a velocity, constant velocity v, and this is happening under the some influence, some external force influence, and we have to calculate the current value in this loop. So how are we going to approach this problem? First, we know that if I can calculate the net EMF induced in this loop, and then I'll just divide that value with the resistance value, I'll get this current value. So all I know is that if I get this E value, then I'll just calculate the I. I'll just divide E by R. So what we have learned so far, that E induced, its magnitude, is basically minus of d phi by dt. This minus comes from the second law of Faraday's law, second Faraday's law, and says that just basically if the d phi by dt is increasing, this is the result of the external field. This minus sign signifies that it will just try to nullify the effect of the external field. So basically this minus d phi by dt is basically d phi by dt mod. So let's calculate the d phi by dt. So at any point of time, let's say this distance is x and the length is given as L. So phi will be equal to what? B, the value is given as b dot dA. What is dA here? dA is basically L into x, this distance x and this length is L. So phi is given as BLX. So in this phi value, this x is changing because this rod is moving forward. So we can calculate this d phi by dt is equal to, this BL is constant, so I'll just keep it out of the differentiation, d by dt of x. So from the kinematics we know that this dx by dt, this rate of change of this length, is equal to this speed, this velocity. So I can write BLV. So this d phi by dt value is BLV mods. So this induced EMF is also this d phi by dt is mod, that is equal to BLV. So we have calculated this induced EMF value. So if I have to calculate this I value, all I have to do is this E by R, this BLV by R. this is the value of the current that is going in the loop. So can we talk about the direction of the current? In this case, is it going clockwise or is it going anti-clockwise? Think about the Faraday's second law and try to understand the direction of the current in this loop.